Hey everyone, welcome to the SCM Analytics YouTube channel. Your go-to place for all SCM related analytical use cases. This is Vicky here, your host for this video. Today, we will be solving the transportation problem for ABC Cosmetic Company by using an Excel spreadsheet solver, optimizing the shipping plan for transporting its products from its plant to its customer warehouses. Let's get started. ABC Cosmetic Company produces various type of its products at its three plants A, B and C. It packs and ships its products in pallets. Plant A and C can supply 30 pallets each month. Plant B can supply a maximum of 40 pallets in a month. Orders have been received to purchase its products from its four customers. Customer C1 wants to order 22 pallets of its products next month. C2 wants 27 pallets. C3 wants 23 pallets and C4 wants 28 pallets. The products will be shipped from its plants to its customers' warehouses, and the cost of shipping each pallet of products have been mentioned in this table. The cost of shipping a pallet from plant A to customer C1's warehouse is $800. Each arrow in the figure represents the shipping route in the network. The management's objective is to determine how many pallets needs to be shipped on its different shipping routes connecting the plants and the customer nodes to minimize the total shipping cost. In these kind of problems, there are usually two types of functional constraints. The amount produced at each plant should be equal to the total amount shipped to its customers. And the total amount received in each customer warehouses should be equal to the total amount ordered by the customer. These type of constraints are called fixed requirement constraints, which makes this problem a fixed requirement problem. Let's now look at the Excel spreadsheet model to construct this mathematical model and solve the transportation problem at hand. Here we have been given the shipping cost and the total supply and demand. The total supply in this case is 100 in the network, and the total demand from its four customers are also 100 pallets. The cells marked in yellow are the decision variables or are the shipping routes where we need to determine how many products will be shipped on a given particular shipping route. The total items shipped from plant A should be equal to 30. Similarly, the total items shipped from plant B should be equal to 40 and the total items shipped from plant C has to be equal to 30. Similarly, on the customer end node, the total amount received should be equal to the total demand placed by the customer. Now let's solve this problem using the Excel solver. Here our objective is to minimize the total cost by changing the decision variables, which is called the shipments, with nothing but the different shipping routes. And we have two constraints, which are the supply and demand constraints. We make the variables non-negative and solve using the simplex linear programming model. On solving the model, we get the following output. From plant A to C1, we ship only 2 pallets and the remaining 20 pallets needed by customer C1 are shipped from plant C. Similarly, for C2, we ship 17 pallets from plant B and 10 pallets from plant C. To meet customer C3 and C4's requirement, we ship their required demand from plant B and A. Plant C is an obvious choice because among all of the cost variables that has been given to us, plant C has the lowest cost. The total cost is 289 euros, 28900 euros, which is nothing but the sum product of the unit costs or the shipping costs in each route multiplied by the units we decide to ship. Now let's look at a slight variation of this transportation problem. Now assume if the supply is greater than the demand, we would tweak this problem in a small variation. This basically means we have excess supply for the network than the total demands generated by the customer. This is often a case when businesses decide to have higher capacities to meet future demand. This is necessarily not a very favorable situation because excess capacity definitely means higher costs for maintaining that capacity. Now we do not go into minor such details for modeling in this example, but in the intermediate course, we will look at a case where we will include those set of constraints to decide on how much supply can be produced. Now let's solve the same problem using the similar constraints that we fed before. When we solve for this equation, we get the same cost as the one before. Now let's look at the third variance to this problem. Is the case when you have higher demand than what you can supply. The total supply in this network is a maximum of 90 and the total demand is 100 pallets. In these cases, in order to meet the fixed requirements, we create a dummy plant. This dummy plant, it can be seen as a virtual plant which balances the model in order to meet the demand constraint. When we solve for this equation, the constraints and the way we are programming the model remains the same. And we get the following output where in order to meet 10 pallets of customer C1's demand, we need a dummy plant. This dummy plant would be then the additional products we need to bring in order to meet the customer demand. The total cost in this case is 249k 100 euros. That's all for today. The contents present in this video are available in the description below. Thank you for watching and I hope this video was useful. Please subscribe to the channel and click on the bell icon for updates on future videos. Until then, take care, bye and happy learning.